How do you solve a really hard problem? I'm talking, of course, about problems that arise in science and engineering, which means that these problems can be converted into a mathematical language and phrased as problems in mathematics. So what I'm really asking is, how do you solve a really hard mathematical problem? No doubt you've encountered many problems in mathematics and you learned many interesting and powerful methods and techniques for solving them. For example, imagine you need to solve a quadratic equation x squared minus 1 is equal to 0. That's a mathematical problem. It's not a very difficult mathematical problem because we have the quadratic formula. It means that we can write down a solution to the general quadratic equation ax squared plus bx plus c is equal to 0. We can write down a formula for the solution in terms of A, B, and C. But what about really hard problems? Like, let's say, how do I solve the problem of sending a Mars rover into space and have it land safely on the surface of Mars without crashing and wasting a stupendous amount of money? That's a really hard problem, obviously. And sometimes even an innocent-looking problem can be really hard. Imagine you need to solve the quintic polynomial equation x to the fifth minus x minus 1 is equal to 0. It looks simple, but it's actually really difficult. It's difficult because there is no formula, like a quadratic formula. And this isn't because we haven't discovered a formula yet. No, this is because such a formula cannot exist. This was proved by the 19th century French mathematician Galois. So how can we solve this equation? Imagine that being able to find a solution to this equation is the difference between safely landing your Mars rover and completely smashing it. So what do we do? One of the most powerful tools in mathematical sciences, which often allows us to solve some really hard problems, is called perturbation theory. Suppose you have a really hard problem. Let's call it HP. The main idea behind perturbation theory is to first interpolate this hard problem HP to an easy problem, let's call it EP, one that you can actually solve, hopefully explicitly using a formula of some sort. And then you describe in a mathematical and systematic way how the solution that you found for the easy problem yields a solution to the hard problem that you're interested in. For example, imagine that you do want to send a rover to Mars. That means you need to launch a rocket into space and take account of all the gravitational forces acting on the rocket by the Earth, the Moon, the Sun, Venus, Mercury, Saturn, and many, many other heavy celestial objects. Well, taking into account all these interactions all at once is extremely difficult. It's basically impossible. The presence of so many of these objects is what makes this problem really hard. On the other hand, if there were no Moon, no Sun, no Venus, nothing at all other than Earth and Mars, then the problem of sending a rover to Mars actually turns out to be rather easy. You can solve it explicitly. So the idea of perturbation theory is to interpolate from the hard problem that we started with many, many celestial objects, all acting on our rocket as it tries to fly from Earth to Mars, to the easy problem where we only have the two planets, Earth and Mars, and then gradually and sequentially add the gravitational contributions coming from introducing all the other celestial bodies. The amazing thing is that this can be done, and it can be done to a remarkable degree of accuracy, enough to land your rover on Mars without crashing it. Mathematically, the meaning of interpolating the hard problem HP to an easy problem EP is to introduce an additional parameter into the hard problem HP, often called the perturbation parameter, denoted by, say, epsilon. What we get is not just a single hard problem HP, but actually an entire collection of hard problem HP sub epsilon, parametrized by epsilon. This must look ridiculous to you. It seems like we've only made things worse, not better, because now instead of trying to solve a single hard problem HP, we need to solve infinitely many hard problems, one for each value of epsilon. But the key behind making perturbation theory work in your favor is to introduce this parameter in a clever way, in a way such that for a special value of epsilon, which is usually taken to be 0, the hard problem HP sub epsilon for this special value of epsilon is an easy problem EP. The technique then is to solve the easy problem EP and sum all the contributions that depend on epsilon. So here's how perturbation theory works in practice. Let's return to our quintic polynomial x to the fifth minus x minus 1 is equal to 0. And imagine that the problem is to find a root of this quintic polynomial. So this is my hard problem HP. But if the linear term in this polynomial weren't there, then the problem would actually be very easy. We would have a polynomial, a quintic polynomial, x to the fifth minus 1 is equal to 0. And this is actually very, very easy to solve. Indeed, if I bring the 1 over to the right-hand side, it's clear that there's an obvious root, which I'll call x sub 0, which is just 1. So this is my easy problem. Now I'm going to use perturbation theory in order to interpolate between my hard problem and my easy problem. And to do this, I will introduce my perturbation parameter epsilon in front of the linear term x. So this is my collection of hard problems. The point is that this collection of hard problems, HP sub epsilon, indeed does interpolate between my hard problem and my easy problem. Because my hard problem HP sub epsilon for the special value epsilon equal to 1 is my original hard problem HP. And also my hard problem at the special value epsilon equal to 0 is my easy problem. So how do we go from a solution x naught of the easy problem EP to a solution of the hard problem HP that we started with? Well, the first thing to say is that x naught equal to 1 is at best an approximate solution of the hard problem. It is certainly not a solution. To find the solution of the hard problem, we need to add all the error contributions that depend on epsilon. Then, using quite simple algebraic manipulations, we can determine these coefficients a1, a2, and so on. This therefore allows us to express the solution x sub epsilon as a power series in epsilon. Finally, in good cases, such as ours here, we can evaluate this power series at the desired value of epsilon, and we can compute the solution x to any desired degree of accuracy. So in this particular example, the solution x is approximately 1.1673. As a research mathematician, I'm interested in understanding why these methods work, especially in much more complicated and abstract situations.